Okay, in the last class we were talking about search engine optimization, and I showed you that document that Google put out that highlighted some of the things you could do. I'm kind of bored of that already, but the main reason I'm moving on to something new today is I want to give you the information that you must have in order to do a good job at assignment 2. So that's the one with the images. So by the end of this week, hopefully, or actually maybe by the end of next week, you'll know an awful lot about how images are stored and how compression works, so that you can do a very good job of talking about them for assignment 2. And then after that I can go back and carry on talking about search engine optimization, or perhaps not, we'll see. You should read the document anyway that I gave you, and maybe if you have read that by the time we go to talk about search engine optimization again, we can get through it more and more efficiently. But I'm mindful of the fact that at the end of the day you have assignments for this module and you want to get the highest marks you can in those. So I want to get everything you need for those out of the way, and then with any time that we've left we can do whatever. And also I want that stuff done as quickly as possible. So that's why we're moving on to something completely different today. However, I do recall warning you of my tendency to do something like that in a module such as this. No. So what we're going to look at today is how black and white images are stored. And that's useful from an understanding point of view. Obviously, if you're going to go storing black and white images, it's useful to know how that happens too. But this is more for the theory than for the practice, okay? And so we're going to look at how images are digitized. So digitizing a black and white image is conceptually quite straightforward, really. Excuse me. Now, by digitization, we mean the process of putting numbers on something, basically. The word digital is bandied about a lot, and it's hard to think of things that aren't digital anymore. But essentially, if something is digital, it just means that it's represented using discrete numbers. Or in practical terms, it's represented using some combination of bits. So how do you go from an image to a bunch of bits that represent that image? Well, when we're digitizing an image, the first thing we do is we break it up into non-overlapping rectangles. They're usually squares, but they don't have to be. They can be rectangles. They would all be the same size. And then the average darkness of each rectangle is calculated. So we look at a tiny portion, and my cursor is always gone. There's no point in my pointing at the screen, is there? We look at each tiny little square, or each tiny rectangle. So this rectangle here, the average lightness or darkness of that would be figured out. Whereas the average darkness of this rectangle here is very different from that one there. Now you can see that if you have tiny squares, you get a finer result, and we call that the resolution. So the number of rectangles you have will have an impact on the resolution and how fine the image is. But in general, we go rectangle by rectangle. How light or dark is this? And if we look at the scale then on the right there, the average lightness or darkness of that rectangle would fit into one of those ranges there. And so that range then is represented by a sequence of bits. We call these here quantization levels. The number of levels you have, the more accurate, the more subtle the representation is going to be. So already in an image, we have 3 dimensions at work already, really. So we have the number of pixels, the number of rectangles that it has. So if I give you an A4 sheet or this huge sheet here, I mean, we could have 1,000 rectangles across and 800 down, or we could have 10,000 across and 8,000 down. Obviously, one would be much finer than the other. However, then, with a black and white image, you also have the number of levels, they're called. And so, if you have 4 bits, you could go up to how many levels? 16. 2 to the power 4 is 16. So, with 4 bits, each rectangle here then could have its average lightness or darkness fitting into one of 16 possible ranges.
Is that all in black and white?
If you've got 4 bits, yeah.
If you got 4 bits.
Yeah. If you've got 1 bit, it's only 2. Well, fax is 1 bit.
Yeah.
Or used to be. Typically, in an image, black and white image, 256 levels is enough. Well, maybe it's enough, maybe it's not, but it comes in, 8 bits is very handy. They come off the shelf in blocks of 8. So, if somebody did some research somewhere and discovered that actually, 270 would be optimal, we'd say screw it for the sake of an extra bit, we'll make do 256. But anyway, so most black and white images are stored with 256. So, I wanted to have you adapt to this kind of conceptually before I start using the words. But many of you are already thinking in terms of these being pixels. So we call those pixels. But what happens is a pixel. So the digital image then is made up of pixels. Okay? And a pixel then stands in for that rectangle that we had. So a pixel you would think after years of doing this I would have a definition of a pixel in my brain somewhere. But I don't.
But wouldn't you class a pixel like the way you used to do newspapers with dots?
No.
No?
No, whole other thing now.
Like a building block of the image.
Yeah. So each of these rectangles is represented by a pixel that has a lightness and darkness equal to the average lightness and darkness of that area in the image. And if you have a large number of pixels, you get a very fine image. And depending on the number of levels, it'll be more faithful or not. So we'll look at some of that. Sorry now for my horrific response to your there's a totally other thing.
Yeah.
Okay. No. So each pixel's color is the same as the average part of the image it represents. No. The more pixels you have then to store the image, the better the quality. I find people struggle with this actually because when you're scanning an image, when you see it on the screen and then when you go to print it, or if you have it like you have an A4 sheet and you put it in a scanner, and then how do you scan it? How many pixels do you use? People struggle with that. If you're printing something, you typically want to be thinking about 300 dots or 300 pixels per inch. It's one of the few things where even in the metric world we still use the imperial units.
Does printers use higher, depending on the printer, they use higher dots?
Oh yeah, I'm just saying 300. I'm saying if you're not going 300 dpi, you're not even at the races. Do you know what I mean?
Yeah.
Like 300 dpi is the minimum you'd want to have. So that means if you have something that is, I don't know, how big is an inch? What's that? That's about 1, 2, maybe that's about 4 inches by 3 inches or something. So, for 4 inches wide by 3 inches high, if you were scanning this to print it, at a minimum you would want 4 by 300 pixels across. And no. So anyway, the more pixels you have, the better the image. But also what's going on is the number of ranges of the possible number of grays that you have is going to have an impact. So we look at those two things, okay? So this image here is 300 pixels, 400 pixels by 300 pixels. If we reduce the number of pixels down, so this one here is 300 by 225. If we come down here then even more, here we're 200 by 150. And if we go a bit further, you're seeing 100 by 75. Now there's actually two things going on here. The PowerPoint or whatever I'm using has kind of smoothed things out a bit using a technique called interpolation, which I'll maybe explain in a second as well.
Blurry.
So it's gone blurry. Instead of going all pixely, it's gone all blurry.
Because the pixels should be basically sharp.
The pixels should be, we should be seeing big, huge, like boxes here. And what we're seeing is blur. That's the operating system or whatever tool, whatever image viewing tool we're doing us a favor, which most of the time works, but when you're trying to explain what pixels are and the pixels getting bigger, it doesn't help. Similarly here, we should be seeing like blocks, not, I think here I forced the point. Okay, that's what we should be seeing as we reduce. So this has a thing called interpolation, where it sort of smooths out the values to help, you know, which is usually good, but not here. So this image here is 40 pixels by 30 pixels, and obviously it's not nearly as good as the, 400 by 300. So resolution is something to consider. Now, so we talked then about bits per pixel, and that's the number of bits, or rather the number of different shades of grey we're going to have. So typically what we do with a black and white image is we have a range with like black on one end and white on the other, and then depending on how many levels we're going to have, we'll break it up accordingly. So if we're only going to have black and white, we might have black on one end, white on the other, and then anything that was up to 50% grey would be just called black, and anything that was more than 50% grey we'd call white. If we had 4 levels, then anything from like completely black to 25% grey we'd call black, or maybe we'd call it 12% grey, whatever, we'll see. But that'd be one level. Anything 75% or higher would be the top one, and then we'd have 2 in the middle from 26 to 50 and 50 to 75. So you could see how if you only had 4 levels, taking all the shades of grey you could possibly have and then saying, well, you're one of those 4 would be a bit harsh. But the question then is how many you can get away with. And the more ranges, the more levels you have, the more pixels you're going to need the more bits you're going to need for each pixel. So we can talk about the number of colors, the number of shades of grey, or we can talk about the number of bits. Generally, like having 7 levels doesn't make much sense, because you would use 3 bits to have 7 levels, but you could have 8 levels for 3 bits as well. So you might as well have 8 levels. Costs the same. So with 3 bits you could have 8 shades of grey. With 5 bits you could have 32 shades of grey. So we'll look at the effect of that. It would be more interesting. So here this image has 256 shades of grey. We're using 8 bits per pixel. If we go down to 7 bits per pixel, we don't see a huge difference. We've got 128 shades of grey. If we go down to 6 bits per pixel, 64 shades of grey. Sometimes you see these things on the big screen quicker than you do in the small one, but I think that's holding out fairly well. I don't think see much of a difference there. We go down to 5 bits per pixel. We're starting to see some banding there in the sky. You see there? So there's only 32 shades of grey here now. Now we'd have a job to count them and pick them out, but there's only 32 kinds of pixel in that image there now. If we go down to 16, 4 bits per pixel, 16 shades of grey. Starting to get more pronounced now. If we go down to 3 bits per pixel, there's only 8. Now, I'd wager we could actually count them. Got that black there. Okay, that's 1. This grey here, 2, 3, 4, 5, 6, 7. So I missed one.
Probably in the sea somewhere.
Probably in the sea. I think the grey there in the sea is somewhere between this shade and this shade, but I'm not sure. But there's only 8 kind of pixels in this image.
Is that what you do, like I say, in Photoshop, when you want to get a picture and go, you know, I want to make it look a bit like a watercolour? Or yeah, got some pixels.
It's more complex than that.
Because that looks like a watercolour now, you know.
Yeah.
It seems like you want to do it very basically, that very good way to do it. It's smoothed out.
Yeah, like the short answer is no, and the long answer is too long.
Not doing
Do you
too
know?
well.
No. But I like questions as long as you like no for an answer. No, it's in Photoshop. Those things are filters, and typically what they're doing is something more sophisticated.
Oh, I know. I'm just saying, if you wanted like a poor man's version of Photoshop,
Yeah.
do it quickly.
Well, I wouldn't call that a watercolor. I call that posterized myself. Actually, you see lots of posters around now. Some of the candidates for the Students' Union have the same graphic designer, and he's done a posterized poster of each of them. That sort of Obama did it last time out. It was very effective.
Oh, it's the kind of
Very few colors. And so you could do that with few. You know, when you're using fewer colors, you get something like that. I think we call it posterized. If we go to 4 shades of grey, can we easily see them? Yeah. So there's the black. Way up there in the top corner, there's that very dark grey, and then there's the grey, and then there's the lightest one. So there's only 4 colors in this now.
Sorry, did you say the 4 colours are including the black and the white?
Yes.
And
So-
the other 2 are just the dark grey and the light white.
Yeah. So that white probably isn't even white. Well, it's clearly not white because the background here is white. So the black looks black, all right. But it's gone for that shade of grey. So there's 4 shades of grey in this image now. Now you notice here we haven't tweaked with the resolution at all. So still the same number of pixels, but the number of possible values each pixel could have is being altered. Okay. And so that's going to have obviously different storage requirements. If you're using 2 bits per pixel and you've got 10,000 pixels, well then that's 20,000 bits. If you're using 8 bits per pixel and you've got 10,000 bits, well then that's way more bits. So reducing the number of colors is one of the ways to change the size of something. And here we've only got 1 bit per pixel. So it's either the dark one or the light one. So if you were to look, if you could sort of zoom in at how this image is being stored, and you could actually see the memory, it would probably be saying something like 1, 1, 1, 1. Each pixel would be just 1 bit. So the first pixel would be just like 1. The next pixel would be like 1. The next pixel would be 1. Eventually you'd come down to these ones here. You'd probably go like line by line like that, Eventually you'd hit a black one there. It's probably the first black one you'd hit. That'd be 0. And then you have a bunch of 1s and 1s again. And so on like that. Now they would of course be stored then as bytes. But if you could see the memory, that's the kind of thing you'd get. So I think a lot of you are kind of just from you can't really live in 2013 and not have some experience of digital images. So a lot of you may know this already, but I want you to sort of start from a different place, and think of it in this way. So you have a number of pixels, and then each pixel is being represented. There's a range of values. So we have black at one end, white on the other, and then we break it up into chunks. And then each area of the image, its average lightness and darkness, fits into one of those ranges, and then we assign it just to the midpoint of that. So So I mean you have a number of students in a class and you're going to give each one a mark, and you might give them a mark between 0 and 100. Or you could just give a mark between like 1 and 10. That's less subtle then. So like you could be a 7, you could be a 6, you could be a 5, 7, whatever. You have different levels of granularity or levels of precision. There was a school of thought that said you should just pass or not. You'd be like, 1, 1, 1, 1, 1, 0, 1, 1, 1, 1, 1, 1, 1. You could just have a 1-bit result instead of a 1 from 0 to 100. If if the nerds had been running the place before, you might have had value from 0 to 256. Your mark could be 0 to 256, or from 0 to 64, or 0 to 128. Whatever. You might say the first bit's the hardest. Whatever.
Every lecture starting the first class with that. The first bit's the hardest.
Yeah, but you could imagine where your pass mark then is like if the first bit in your result is a 1, you've passed. If it's a 0, you fail. And then the rest. Yeah. Anyway, I digress. Okay. What I'm saying is that in terms of storing things, in terms of storing real world values, you have choices. Okay. So if I was to line you up against the wall and measure your heights. Okay. Actually, could you stand up against the door for me? Honestly, yeah. No. So, you can look at us. It's all right. Yeah. So we could get out a ruler, okay, and measure his height, right? And I don't know how tall are you?
What use your centimeters?
Oh, centimeters. Yeah.
189.
Right, so he's about 189. Okay. So if I was telling you, if he mugged me or something and I was telling the policeman his height, I mean, I probably wouldn't say, well, he's, 1.892741 meters. Do you know what I mean? That level of precision, we don't need that level of precision to think about a person's height. If I was, if I was launching him at the moon, then, I might need that kind of precision. So depending on the context, you need different levels of precision. Similarly, at home, if you're measuring something, if you want to know if that couch is going to fit there, you might just, take steps and see. We could measure his height, in how many A4s is he? And so if I wanted to record all of your heights, I could just record your heights, as you're like probably 1, 2, 3, 4, whatever. You're probably, 6 or 7 A4s. So he just like.
So beer cans.
Beer cans we do 2, 1,
Drink your fate in
2, 3, 4, 5, 6, 7. Okay, so he's in like the 7th A4 sheet, right? I could probably, everybody would probably be like 1 to 8 anyway. So in terms of measuring your height in A4 sheets, it's a different level of precision, which would take a different number of bits. Another way would be just measure how many bricks you are. 1, 2, 3, 4, 5, 6, 7, 8, 9. We might say you're the 10th brick even. Okay? So every time it just be 1 brick. You just fit into one of those values. And so from that information then to get your heights back, we'd probably just use the midpoint of the brick. And say, well, that's the midpoint, and he's plus or minus, somewhere in that range. Okay? So we do the same with the shades of grey. Thank you, sir. You may sit. You're very tall. No. What? Tall.
That's the word close to this. It's German for great.
Oh no, it's German for monastery.
There we go. That was close.
Okay. Lost. Anyway. No. He's a person in his own right as well. He's not the German in the class.
Yeah. So when it's like things like horses and hands and you're saying you can use whatever you want to do For the heights of things.
The difference really, what I'm talking about is the level of granularity, what we actually call the number of quantization levels. So if you're going to assign someone, if you're going to fit someone into one of those slots, how big are the slots? So for a person's height, we work in sort of 1 centimetre slots. We're happy enough with that. In casual conversation, actually, if people are using imperial units, usually we're talking just feet, or feet and a half. I mean, if someone is, 5, 5, 6, 6, whatever. Just saying the number of quantization levels that you have affects the precision of your recording of the value. So those are fairly big bricks. If we had smaller bricks, we'd have more precise measurements of his height. And so similarly, when it comes to a shade of grey, the number of quantization levels that you have, the number of possible shades of grey, is going to affect the fidelity of the recording, the image. Did you get the idea? So aside from the number of pixels giving you more precision, the pixel depth, we call it, the number of bits per pixel, is going to affect the quality as well. So if this image cost €8 to send with your roaming carrier from whatever your hut in Thailand, this one would only cost €1 to send. So this is 1/8 of the size of the original. Now, you could pay €8 for this one, or €7 for this one, or €6 for this one, or €5 for this one. I'd probably pay the €6. I think the €7 and €8 is bad value. I don't think you get much extra for your money.
5 just starts the banding.
Yeah, the 5 just kind of starts to give. But it depends, how many I was sending as well.
Yeah, it
Depends on the context.
It's completely dependent
on the context. If you're sitting on the beach in Thailand and you want your friends to be jealous, you want to post this to Facebook. It depends. If you're going to send it to a bunch of people, the difference between €3 and €8, and the difference between €30 and €80 is a lot. Also, if this is a scan of your brain and they want to send it to some expert in Sydney who can tell whether you've got cancer or not, they say, well, we can spend €80 on this one, or look, if you want, we could just, for a tenner, we could send this one. You'd say, take the money. So it'll depend on the context as well. But there are things that are clearly better value than others. And that's one of the things we consider when we're saving images to web pages. As time has gone on, I think that the cost of bandwidth and storage has gone down so much that I think people involved in making web pages don't spend quite as much time stressing out over every image as they used to. But I think it's good to know how these things work. And also, certainly for mobile, if something is going to take 8 seconds to download instead of 1, well, that's a long time. So, if a grayscale image, a black and white image, had 400 pixels by 300 pixels, and it had 250 shades of grey, what size might you expect it to be? So, have a think about that one. And not in the abstract sense. So how many pixels are there? That's the first thing you need to know. And the answer is not 1200. 400 by 300 is not 1200. Now you're allowed to use pens and paper and stuff.
$20,000?
Well, the question is, what size would it be?
do you mean? It's a 400 by 300?
It's got 400 pixels across and 300 pixels
So it's
down.
1200 pixels, isn't it?
Well, no, I just said now 300 pixels by 400 pixels is not 1200 pixels.
20,000 pixels.
It's 12 with 4 knots.
120,000.
Yeah, yeah.
So, and then what?
So 120,000 pixels.
That'd be 8 bits per pixel, then, would it?
Well, 256 shades grey is going to need 8 bits per pixel.
So, would you times that by 18?
You could say 120,000 bytes is probably what you're looking at.
120,000 bytes.
Yeah. Yeah.
Did you not factor in the 8 bits?
No, 8 bits per pixel.
Yeah.
8 bits is 1 byte. So you could multiply the number of bits and then divide by 8 to get the number of bytes.
Oh, yeah.
But you'd be, you know,
12 bits,
yeah. That's only because it's 8 bits. If it was something else, you wouldn't have much of a choice. So you got 256 colors, which is 8 bits per pixel. You've got 120,000 pixels, which by 8 would give you 960,000 bits, which would be 120,000 bytes, which would be how many kilobytes?
12,000.
120 kilobytes?
It's not quite now. Has someone not done this with you, no?
Well,
Right.
1,000 bytes now isn't a kilobyte.
1,024.
A kilobyte is 1,024 bytes.
So 117.18?
Whatever it works out to be. I don't know. But anyway, 120,000 bytes is a perfectly reasonable answer as well. What if it was 256 pixels by 256 pixels and had 100 shades of grey? So how many pixels do we have? And then how many bits do we need for each pixel? So what's 256 by 256? How many pixels is that?
65,536.
I divided by 100, don't you?
Well, that's how many pixels. Now, how many bits do you need to represent 100 possible values?
7.
Because 8 will give you 256. 7 bits would give you 128 possible values. So in 7 bits, you have enough there. So each pixel would only need 7 bits to represent it. And you've got 256 by 256 pixels. So how many bits does that work out at? Works out at 458 odd bits. Which would be that many bytes. Which works out at 56k bytes. So if that stretched you, maybe today now wasn't hugely successful from my point of view.
I got 56k in the end anyway.
Yeah, yeah,
You multiplied by 7, then you divided by 8 again, didn't you?
yeah, yeah.
To get to the proper bytes, and then you divide by 1,024 to get the kilobytes.
Yeah, I don't know though how you would come by this by another route, because you do have to multiply by 7.
It's pretty tricky to jump past it, though, isn't it?
I don't see how though you could go anywhere other than, like, I guess you could, 256 by 256 by 7 divided by 8 and come up with the answer straight away.
That's what it did, yeah.
Okay.
And then divided by 1,024 to get the kilobytes.
Yeah. So depending on the number of possible values that you can have, you will require a different number of bits. I didn't drive that point home enough So suppose I was too lazy to learn your names and I just wanted to assign each of you a bit code. So I could go like 0001, you know, what's the answer to this question? 010, what did you get for this? How many bits would I need today? If I was to put stickers on your head, if I had like 0 and 1 stickers and I want to put them on your forehead, how many? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
8 bits, I suppose. Oh, 5 bits.
14 people here.
So 4 bits.
So with 4 bits, if you had 3 bits, you could do 8, couldn't you? 4 bits, you could do 16. So with 4 bits, I could give each of you your own number. So you could have hoodies with just, you know, a 4-bit code. No. However, that's of course if it's just you guys. But the class as a whole, how many people in the whole class? How many people in DNETDCOM altogether?
It'd still be okay with 32.
Well, that's the question, isn't it, I suppose? Is there more or less than 32? I would say there's just less than 32.
Just 5 would do the whole thing.
So 5 bits then would do the whole thing. So you could be 0, 0, 0, 0, 0, 0, 0. You could be 0, 0, 0, 0, 1. You could be 0, 0, 0, 1, 0. You could be 0, 0, 0, 1, 1. And so on. And with 5 bits, I'd have enough to give everyone their own code. So as an exercise then, if we were to give everyone on the planet their own bit code, how many bits would we need per person?
64 bit would do it anyway, that's for sure.
You know? And the question becomes, if you want to give each machine on the planet its own bit code, how many bits do you need? And that's a question you have to deal with in networking. So if we assume 5 billion people, give or take, you know, how many bits do we need? So figure that out between this class and the next.